You think you know how this would happen. Everybody will float away. The atmosphere will drift off into space. The oceans will rise. Buildings will topple over. It will be dramatic and it will be cinematic. Every depiction of this in various media, movies, YouTube videos, and classroom thought experiments is inaccurate. Not just slightly inaccurate, completely inaccurate, and in a manner that shows you something about gravity as a force and how it affects matter and gives you the definition of the word loses when you are talking about a force that has been affecting everything around you since before Earth existed. By the end of the evening, you will have a more complete understanding of gravity than what would be portrayed in any movie, documentary about a disaster that has occurred. If your thing is watching videos that show you the real answer to a question that you thought you knew the answer to was not only completely different from what you thought, but also really weird and troubling, I'd really appreciate you to click on like and subscribe, because that helps more than you can ever know. So get comfy and settle in, because we're going to start. Most people think that gravity is a force that pulls everything toward the center of the Earth. So when gravity is off, nothing pulls toward the center, so everything can float. Drama is created in this imaginary example of flipping a switch. Gravity is on, everything stays put. Gravity is off, everything floats calmly away. There may be a little chaos. Occasionally things that stand cannot stand any longer and fall sideways in a confusing direction. However, the main theme is that things go up instead of down, and that's the problem with this imaginary example, because this where this theory is wrong. Gravity is not a force that pulls things down. That description, which has been repeated in classrooms for centuries and is technically derived from Newton's work, is a useful approximation for everyday engineering and navigation, but it is not what gravity is. Gravity is the curvature of space-time caused by the presence of mass. Every object with mass curves the space-time around it, and other objects follow the curves in that space-time. What we experience as being pulled toward Earth is actually us following the curve in space-time that Earth's mass has created. The apple doesn't fall because Earth grabs it. The apple falls because Earth has bent the geometry of the space-time region the apple occupies, and the apple is following the straightest possible path through that curved geometry, and that path leads toward Earth's center. This distinction matters for what we're about to discuss, because losing gravity means something very specific and very strange when you understand what gravity actually is. You cannot turn off gravity the way you turn off a light. Gravity is not generated by a mechanism that can be switched off. It is a geometric consequence of mass. As long as Earth has mass, it has gravity. The only way Earth loses its gravity is if Earth loses its mass, which is a very different kind of catastrophe from what most people imagine. But let's set that aside for a moment and engage the thought experiment on its own terms, because the thought experiment is worth following carefully. Let's ask, what would actually happen if somehow Earth's gravitational field were reduced to zero, if the curvature of space-time around Earth suddenly flattened out? What would the sequence of events look like, starting from the first fraction of a second? The first thing to understand is that gravity does not just hold you to the surface. Gravity holds everything together. Every atom of Earth's rock, iron, and silicate is held in place partly by chemical bonds and partly by gravity. The planet itself, its roughly spherical shape, its layered interior, its solid crust over a molten mantle, over a liquid outer core, over a solid inner core, exists in its current configuration because the gravitational attraction between all its parts holds it together against the thermal and chemical pressures trying to push it apart. Remove gravity, and you don't just remove the thing holding people to the surface, You remove the thing holding the planet together. Earth is not a solid ball in the way a bowling ball is solid. It is more like a very large, very hot, very high-pressure system that has organized itself into concentric shells as a result of billions of years of gravitational sorting, heavier elements sinking toward the center, lighter elements rising toward the surface, all of it held in a dynamic but stable configuration by the enormous gravitational pressure squeezing everything together. The pressure at Earth's center is about 3.6 million atmospheres, 3.6 million times the pressure of the atmosphere at sea level. That pressure exists because of the weight of the overlying material, which exists because of gravity pulling all that material toward the center. Remove gravity, and that pressure disappears instantly. And here is where the thought experiment immediately becomes more violent than any movie has ever shown. Because the consequence of removing 3.6 million atmospheres of pressure from the interior of a planet is not a gentle expansion. It is an explosion. The iron and nickel of the inner core, which currently exist as a solid only because the gravitational pressure is high enough to force them into a solid phase despite temperatures of 5,000 to 6,000 degrees Celsius, temperatures higher than the surface of the sun, would instantly transition from solid to liquid to gas. The outer core, already liquid, would flash to vapor. The mantle, currently a high-pressure solid that flows like a very viscous fluid over geological timescales, would expand explosively. The crust would be shattered and thrown outward by the energy released from the suddenly depressurized interior. The scale of this explosion is genuinely difficult to express. Earth's gravitational binding energy, the total energy required to completely disperse all of Earth's material against its own gravity, is approximately 2.5 times 10,332 joules. That is the energy of $60 trillion of the largest nuclear weapons ever detonated, released all at once. If gravity were turned off instantaneously, Earth would not gently come apart, it would detonate. The material that had been Earth would expand outward at velocities determined by the thermal energy suddenly released from the depressurized interior, velocities measured in kilometers per second. Within seconds, the surface would be moving outward. Within minutes, the organized structure of the planet would be gone. Within hours, the debris would be dispersing through the inner solar system. There would be no floating gently up into the air. The ground itself would be moving outward, faster than any surface object could track. You would not experience weightlessness. You would experience an explosion. But this is the most extreme version of the thought experiment. Instantaneous, complete removal of gravity. Let's slow it down. Let's ask what happens if gravity weakens gradually over a period of time, long enough to observe the sequence of effects before everything comes apart. This version is still not possible in any physically realistic scenario, but it gives us a more useful analytical tool for understanding what gravity actually does to every system it touches. The first effects of weakening gravity would be felt underground, not on the surface. The interior of the Earth is under enormous pressure that is, as we just discussed, entirely gravitational in origin. Even a small reduction in Earth's gravity would reduce the pressure in the deep interior, causing the material there to expand slightly. This expansion would propagate upward through the mantle and crust as a pressure wave. The crust would flex. Tectonic plates, which are currently held against the mantle by gravity, would begin to respond differently to the mantle's behaviour. Volcanic systems, which are driven partly by the pressure differential between the deep interior and the surface, would change in character. The magma that rises through volcanic conduits does so partly because of pressure from below and partly because of buoyancy. Molten rock is less dense than solid rock, so in a gravitational field it rises. Reduced gravity and the pressure from below decreases, but the buoyancy driving force also decreases. The balance of forces in volcanic systems would shift in complex ways. The oceans would be the first surface feature to visibly respond. Water is a liquid, and liquids respond to changes in the gravitational acceleration that determines their weight far faster than solid rock does. The surface of the ocean is currently maintained in its roughly horizontal configuration by gravity. Water flows from high areas to low areas until it reaches an equilibrium surface. Reduce gravity and the equilibrium surface changes. The effective height of the ocean surface would rise relative to sea level because the weight of the water column would decrease. Coastlines would begin to flood, not because sea level rises in the traditional sense, but because the water's tendency to run downhill weakens. Rivers would flow more slowly, lakes would develop higher banks relative to their shorelines. Water in pipes and aqueducts would require less pumping pressure, then no pumping pressure, then would begin to flow in unexpected directions as gravity's guidance weakened. The atmosphere would also begin to change immediately. Earth's atmosphere is held in place by gravity. The air pressure at sea level is approximately 101,325 pascals, which is the weight of the air column above each square metre of surface divided by the area of that surface. As gravity weakens, the weight of the air column decreases, and the pressure gradient that keeps the atmosphere from expanding into space becomes shallower. The atmosphere would begin to expand vertically, not immediately into space, because molecular speeds at room temperature are much lower than escape velocity, but upward, gradually. As the balance between the thermal pressure of the gas and the gravitational force holding it down shifts, the sky would not immediately change colour, the air would not immediately thin. But the upper atmosphere would expand, the stratosphere would grow, and the density of the air at high altitudes would increase relative to what it currently is. The immediate effect on human beings of reduced gravity, not zero gravity, just reduced, would be disorienting in ways that go beyond the obvious. Every physical intuition you have is calibrated for 1 gram. Your sense of balance, the feedback loops between your vestibular system and your motor control, the way you unconsciously compensate for gravity when you walk, reach, throw, or even hold a cup of coffee, all of it is tuned to Earth's gravitational acceleration of 9.8 meters per second squared. Reduce that to 0.8 grams, which is 80% of normal, and experienced climbers have trouble on stairs. Reduce it to 0.5 grams, and most people lose the ability to maintain confident upright balance within minutes of the change, because their postural reflexes are trained on 1 gram and cannot immediately compensate for a force they have never experienced. The Mars gravity of about 0.38 grams, which is the gravitational environment human beings would first encounter if we ever establish a presence on Mars, produces significant physiological consequences, even in astronauts who have trained for years. Bones and muscles calibrated to 1 gram do not maintain their integrity at lower gravities. The heart, which pumps blood against gravity to reach the brain, becomes oversized for its gravitational environment and begins to atrophy. Fluid distribution in the body shifts, causing characteristic face puffiness and leg atrophy in microgravity environments. All of this would begin happening on Earth if gravity weakened, even gradually. The physiological consequences of reduced gravity are not subtle over the timescales of weeks and months. They are measurable and significant. Long before the planet itself began coming apart, the human beings on its surface would be experiencing the medical consequences of living in a gravitational environment different from the one their bodies evolved for. But let's push further. Let's move toward the genuinely dramatic end of the spectrum. Not a gentle weakening, but a rapid reduction to something close to zero. What happens to the major systems that gravity currently governs? Two major systems. Water first, because water is everywhere, and because its behavior at low gravity is both counterintuitive and important. In zero gravity, water does not pour, it does not flow, it does not have a natural direction of movement at all. Water in zero gravity forms spheres, roughly spherical droplets, determined in size by surface tension, because in the absence of gravity, surface tension is the dominant force determining the shape of a liquid body. The International Space Station provides our best observational data for this. Water, released in the station's interior, forms trembling spheroids that migrate slowly through the air, coalescing when they meet, splitting when disturbed, following no direction that a person standing in normal gravity would predict. Applied to Earth's oceans at zero gravity, the first effect would be a massive, rapid rise of the ocean's surface. As gravity decreased, the weight of the ocean water, which currently keeps it pressed against the ocean floor and shaped by the curvature of the ocean basins, would decrease. If oceans had fallen slowly, the ocean water would begin to expand upward and outward, following the newly reduced pressure gradient. Coastal regions would be inundated almost immediately, not by a wave, but by a broad, slow lift of the entire ocean surface. The ocean basins would become shallower as the water expanded vertically. Island nations would disappear within minutes. Coastal cities would flood in the same time frame. The water would not stop at sea level plus a few meters. It would keep rising as gravity continued to weaken, because there is no new equilibrium for the ocean's surface in a world of changing gravity. The ocean is not an autonomous system with a will of its own. It is a fluid governed entirely by the forces acting on it, and in a world of decreasing gravity, those forces change continuously. At very low gravity, a few % of normal, the ocean's surface would have risen tens or hundreds of meters above current sea level, drowning everything at low elevation. Then, as gravity approached zero, the ocean would transition from a surface-hugging layer to a three-dimensional cloud of water. The water would not instantly fly off into space. The escape velocity from Earth decreases as gravity decreases, but the water molecules are moving at speeds determined by temperature rather than gravity. And at room temperature, water molecules have average speeds of about 600 meters per second, which is below the current escape velocity of 11.2 kilometers per second, but well above the escape velocity of a planet with nearly zero gravity. The water would evaporate into space, not immediately, not all at once, but progressively, as the escape velocity dropped toward values that individual molecules could achieve through thermal motion alone. The atmosphere would follow a similar but faster trajectory, because atmospheric gases, nitrogen, oxygen, carbon dioxide, have lower molecular masses than water and therefore higher average molecular speeds at any given temperature. The lighter gases would begin escaping first. Hydrogen, which exists in small quantities in the upper atmosphere, would escape almost immediately once gravity dropped below a certain threshold. Helium would follow. Then the heavier gases would begin to escape from the upper atmosphere, the thermosphere and exosphere, and the process would proceed downward through the atmospheric layers. This is not a gentle process. The current atmosphere provides several services simultaneously. It provides the pressure that allows liquid water to exist at the surface. It provides the oxygen that terrestrial life breathes. It provides the greenhouse effect that keeps the surface temperature within the range where liquid water can exist, and it provides the shield that burns up incoming meteoroids before they reach the surface. Remove it, and you remove all of these simultaneously. Before the atmosphere is fully gone, the surface conditions would become unsurvivable. As atmospheric pressure dropped below the triple point of water, the pressure and temperature at which water can exist in all three phases simultaneously, which occurs at about 612 pascals, liquid water would no longer be stable at room temperature. It would either freeze or boil, depending on the temperature. The transition would not be orderly. In some locations, water would flash boil as the pressure dropped below its vapor pressure at local temperatures. In others, it would freeze as the evaporative cooling of rapidly evaporating water. The surface of the Earth would become a place where water could not exist in liquid form, which is the same as saying a place where life as we know it could not survive, regardless of what else was happening. The temperature effects would compound the problem. The greenhouse effect, the process by which atmospheric gases, particularly carbon dioxide and water vapor, absorb outgoing infrared radiation and re-emit it back toward the surface, keeping the surface warmer than it would otherwise be, depends on having an atmosphere. Remove the atmosphere and the greenhouse effect vanishes. Earth's equilibrium temperature without its atmosphere is approximately -18 degrees Celsius on average, cold enough that the entire ocean surface would eventually freeze if the ocean was still there. Of course, by the time the atmosphere is gone, the ocean is also gone. So the surface temperature question becomes somewhat academic. The surface of Earth, stripped of atmosphere and ocean, would look much like the surface of the Moon, or, more precisely, much like the surface of a moon would look if it happened to be at Earth's distance from the Sun, which gives it a dayside temperature of around 120 degrees Celsius and a nightside temperature of around -170 degrees Celsius, with no atmosphere to moderate the difference. Humans on the surface, any humans who had somehow survived to this point, which is vanishingly unlikely given everything preceding it, would face immediate death from any of several causes simultaneously. Asphyxiation from the disappearing atmosphere, exposure to unfiltered solar radiation, including UV, X-rays, and particle radiation, the mechanical effects of the pressure differential between the interior of the body and the near-vacuum environment, and the temperature extremes of direct sunlight versus shadow with no atmospheric moderation. But all of this analysis has been treating gravity as an external force that can be removed while everything else stays the same. The deepest problem with that framing is that gravity is not external. It is constitutive. Gravity is part of the physical reality that produced everything we are describing. The atoms in your body, the planet beneath your feet, the stars in the sky, the structure of the universe on every scale above the size of an atomic nucleus, all of it has been shaped by gravity over billions of years. Removing gravity doesn't just change what happens next, it invalidates the history that produced the current state of things. Consider what gravity actually built. The solar system formed about 4.6 billion years ago from a cloud of gas and dust, the solar nebula, that was itself the remnant of a previous generation of stars that had lived and died. Synthesizing heavy elements and dispersing them into the interstellar medium. This gas and dust cloud began to collapse under its own gravity. As it collapsed, it spun faster. Angular momentum is conserved, so a collapsing rotating cloud speeds up. The same principle that makes a spinning ice skater rotate faster when she pulls in her arms. The center of the collapsing cloud grew denser and hotter, eventually igniting nuclear fusion and becoming the sun. The outer regions of the cloud flattened into a disk, and within that disk, gravity caused small particles to clump together, growing from dust grains to pebbles to boulders to planetesimals to planetary embryos to planets. Earth is the product of this gravitational aggregation process, which took approximately 50 to 100 million years to produce a planet of roughly its current size. The layered interior structure of Earth, the iron core, the silicate mantle, the continental and oceanic crust, formed through a process called differentiation, which is also gravitational. In the early Earth, shortly after formation, the planet was largely or entirely molten due to the heat of accretion, the impacts of the planetesimals and embryos that built the planet, and the heat generated by the decay of short-lived radioactive isotopes. In this molten state, gravity sorted the materials by density. Denser iron and nickel sank toward the center, forming the core. Lighter silicate materials rose toward the surface, forming the mantle and crust. The result is the layered Earth we inhabit, a structure that exists because gravity has been sorting material by density for 4.5 billion years. The water on Earth's surface, the oceans, rivers, lakes, glaciers, and water vapor in the atmosphere may have arrived partly from asteroids and comets in the early solar system, and partly from outgassing of the planet's interior as it cooled. But its persistence on the surface is governed by gravity. Earth's gravity is sufficient to hold on to water molecules in the atmosphere, despite the thermal motion that would otherwise allow them to escape to space. Earth gravity. Mars, with about 38% of Earth's gravity, has lost most of its water over geological time. The lighter water molecules in the upper atmosphere achieved escape velocity and were lost to space. The Moon, with about 16% of Earth's gravity, has essentially no atmosphere and no liquid water on its surface, for the same reason. Life and death. Earth's gravity is in a sweet spot, strong enough to retain water and the gases that make up the atmosphere, not so strong that it prevents the lighter gases from ever escaping, creating the atmospheric composition that life has evolved to breathe and depend on. The Moon itself is a product of gravity, not just Earth's gravity, but the gravitational dynamics of the entire early solar system. The giant impact that created the Moon 4.5 billion years ago, the collision of Earth with a Mars-sized protoplanet, was the consequence of a gravitational configuration in the early solar system that sent that proto-planet on a collision course with the proto-Earth. The debris from the collision, ejected into Earth orbit by the energy of the impact, was then gravitationally assembled into the Moon over a period of years to decades. The Moon's current orbital configuration, its distance from Earth, the rate at which it is receding from us, the tidal effects it exerts on Earth's oceans, and even on Earth's solid interior, all of this is governed by the gravitational interaction between Earth and Moon. A system that has been evolving since the Moon formed and will continue to evolve for billions of years. Remove gravity from Earth, and you don't just remove the force holding you to the surface. You unwrite the entire history that produced the surface you're standing on, the air you're breathing, the water in the oceans, and the planet itself. You are not describing a world like ours minus one ingredient. You are describing a situation that is physically incoherent, a configuration of matter that could not exist, because the matter in that configuration was assembled by gravity and could not have reached its current state without it. This is the deepest lesson of the gravity thought experiment, and it's one that most treatments of the subject don't reach. Gravity is not a feature of the world, it is the architect of the world. You cannot remove the architect and keep the building. Now let's go somewhere more speculative, because thought experiments are valuable not just for the physics they reveal, but for the thinking they force. Let's say we grant the scenario full physical license. Gravity goes away, somehow, in a controlled way that allows us to watch the sequence of events unfold, without the whole thing immediately becoming an explosion. What is the actual sequence from moment zero to the point where Earth is unrecognizable? Moment zero. Gravity switches off. Every object on the surface, people, cars, buildings, trees, water, soil, begins to drift upward from the surface because the surface itself is no longer pulling them down. The rate of drift is slow at first. Without gravity providing an upward force, the objects simply follow the trajectories they were already on, minus the gravitational component. A person standing on the surface at the moment gravity switches off is initially standing still relative to the surface. They don't immediately fly upward. They become weightless. They feel the absence of pressure under their feet. They slowly, without any horizontal acceleration, begin to drift away from the surface in whatever direction they were oriented at the moment gravity ceased, which for a person standing upright is upward. The sensation would be immediate and unmistakable. Every person on Earth's surface would simultaneously experience the loss of the feeling of weight, the pressure of the ground against their feet, the tension in their muscles required to maintain posture, the familiar sense of being pressed toward the floor. That would be replaced by the sensation astronauts experience in microgravity, a complete absence of the pressure that tells your body which way is down. The vestibular system, the inner ear's gravity sensing apparatus, would immediately report that the input it expects, the linear acceleration signal corresponding to 1 gram downward, has ceased. This produces immediate disorientation, typically accompanied by nausea. Virtually every person on Earth would simultaneously feel motion sickness. Within seconds, the drift away from the surface becomes perceptible. Loose objects, anything not fastened down, begin to drift. The dust on surfaces lifts. Papers on desks rise slowly. Coffee in open cups develops a thin film of liquid that floats upward from the surface. Water in rivers and oceans begins to behave differently. The rivers would first stop flowing, because flowing is a response to gravity, and then begin to break up into clouds of droplets as surface tension takes over from gravity as the dominant force shaping liquid water bodies. Within minutes, the situation becomes alarming in practical terms. Buildings, designed for a gravitational environment, are not designed for the forces now acting on them. The foundations of buildings are designed to transmit the weight of the structure into the ground. In a world without gravity, the compressive forces that foundations are designed to handle are replaced by different forces, primarily related to the structure's tendency to drift and rotate. Buildings don't immediately collapse. Collapsing requires gravity, but they would begin to behave strangely, rotating and drifting at their anchorage points, potentially causing structural failures at joints and connections designed for compression rather than tension. Trees would begin to uproot themselves, not from any force applied to them, but from the absence of the force that was pressing their root systems into the ground. The soil itself would begin to behave like a fluid in slow motion, individual particles losing the gravitational compression that held them together and beginning to drift apart from each other. The ground beneath your feet would become unreliable within minutes, losing the compaction that makes it solid. Within hours, the large-scale consequences become dominant. The ocean, as described earlier, would be spreading outward and upward in a vast, slow expansion. The atmosphere would be noticeably thinner at the surface as it expanded upward. The temperature would be dropping as the insulating and heat redistributing properties of the atmosphere were compromised. 1. The sky would be darkening, not because the sun was setting, but because the atmosphere was becoming less effective at scattering sunlight. The blue sky colour depends on the density and composition of the atmosphere. And a less dense atmosphere would produce a darker, more purplish sky, transitioning toward the black of space as the density continued to fall. Within days, the planet's surface would be recognizable only in its geography. The water would be gone or going. The air would be dangerously thin. The temperature at night would be plunging towards space temperatures, and the temperature in direct sunlight would be rising as the atmosphere's moderating influence declined. Any life on the surface that required liquid water would be dead or dying. The exceptions would be life in sealed environments. Submarines, still underwater if any water remained. Sealed habitats, any structure that maintained internal pressure and temperature independent of the external environment. Within weeks, the planet's structure itself would be compromised. The interior of the Earth, decompressed by the loss of gravitational pressure, would have begun to expand. The mantle, which under normal conditions flows extremely slowly, but is effectively solid on human timescales, would behave more fluidly as the confining pressure decreased. Volcanic activity would change character. Drastically, volcanic eruptions are already partly driven by the pressure difference between the deep interior and the surface, and that pressure difference would shift dramatically as the surface pressure dropped to near zero and the interior pressure began to relax. The tectonic plates, freed from some of the gravitational forces that drive their motion, would behave unpredictably. Within months to years, the planet itself would begin to come apart. The rocky material of the mantle and crust, no longer held together by gravitational pressure, would expand and disaggregate. The iron core, no longer kept solid by the crushing pressure of the overlying layers, would expand and vaporize. The planet would transition from a coherent, spherical body to an expanding cloud of rock, dust, metal vapor, and gas, the same raw materials that, 4.6 billion years ago, were assembled by gravity into a planet in the first place. The sun's gravity would still be acting on this cloud of material. The debris would not simply disperse into interstellar space. It would orbit the sun, gradually spreading out into a debris ring in Earth's orbital path. A ring of material similar to the asteroid belt, but composed of the remnants of what was once a living world. Over millions of years, some of this material might reaggregate under its own gravity into smaller bodies. Some might be perturbed into new orbits by Jupiter and the other planets. Some might fall into the sun. The material of Earth would persist, scattered and transformed, for as long as the solar system itself persists, billions of years. But the Earth, as an organized, coherent, habitable world, would be gone within a timescale measured in years from the moment gravity ceased. Now, I want to take a step back from the disaster sequence and ask a question that the disaster sequence makes it easy to overlook. What does this tell us about why gravity matters? The most important thing that the gravity thought experiment reveals is not the drama of the destruction. It is the comprehensive, foundational role that gravity plays in every physical system we interact with. Gravity is not one of the forces that shapes our world. It is the force that made our world possible, and it is the force that continues to maintain our world in the configuration that makes it habitable. Start with biology. Every living organism on Earth has evolved in 1 gram, not approximately 1 gram, not 1 gram plus or minus a significant margin. Exactly the gravitational field that Earth currently produces, which varies slightly from place to place due to local differences in the density and distribution of rock, but which is essentially constant over any timescale relevant to biological evolution. The bodies of living organisms are shaped by gravity in profound ways that we only appreciate when gravity changes. Human bones are a clear example. Bone is a dynamic tissue. It is continuously being remodeled, with osteoclasts breaking down old bone and osteoblasts building new bone, in a process that is regulated by the mechanical loads the bone experiences. In a 1 gram environment, weight-bearing bones like the femur, tibia, and spine experience regular mechanical loading that stimulates bone deposition. Reduce the mechanical load, as happens in microgravity, and the osteoclasts continue their work while the osteoblasts receive fewer signals to build, resulting in net bone loss. Astronauts on the International Space Station lose approximately 1 to 2% of bone mass per month in key weight-bearing regions. An astronaut on a 6-month mission can lose up to 10% of their hip and spine bone density, equivalent to roughly a decade of age-related bone loss, compressed into 6 months. Some of this is recovered after return to Earth, but not all. The Far Curiosity system is similarly calibrated. The heart pumps blood against the pressure gradient created by gravity. Blood in the legs must be pushed upward against the gravitational force to return to the heart. In microgravity, this pressure gradient disappears, and the heart adapts by becoming more efficient at the task it no longer needs to perform, which means it becomes less capable of performing it. When astronauts return to Earth, they often experience orthostatic hypotension, a drop in blood pressure when they stand up that causes dizziness and sometimes fainting, because their cardiovascular systems have adapted to microgravity and are no longer able to maintain adequate blood pressure against Earth's gravity immediately. These adaptations happen on timescales of weeks to months. They are the biological response to a change in the gravitational environment. They reveal that biology is not just shaped by gravity in an evolutionary sense, the long, slow process of natural selection optimizing organisms for 1 gram, but in a continuous physiological sense. Living bodies are constantly responding to and calibrated by the gravitational environment they inhabit. Change the gravitational environment, and the body begins to change in response within days. The agricultural and ecological systems that support human civilization are equally gravity dependent, though in less obvious ways. Plants grow toward the light and away from gravity, a phenomenon called phototropism and gravitopism, respectively, governed by hormone gradients that the plant establishes in response to the direction of the gravitational force. Remove gravity, and plants lose their directional growth signals. Their roots no longer know which way is down. Experiments on the International Space Station have shown that plants can grow in microgravity. Life finds ways, but their growth patterns are abnormal, and their productivity is reduced compared to the same plants in one graph. Agriculture in a significantly reduced gravitational environment would require fundamental redesigns of cultivation methods. Water delivery to plants depends on gravity. The movement of water through soil, capillary action competes with gravitational drainage to determine how water is distributed in the root zone, changes when gravity changes. The evapotranspiration cycle, by which water evaporates from plant surfaces and soil, rises in the atmosphere, condenses into clouds, and falls as rain, is governed by gravity at every stage. Evaporation pushes water vapor up. Gravity pulls it back down. The balance between the two determines atmospheric water content, cloud formation, and precipitation. Reduce gravity, and the water cycle changes. Rain falls more slowly, rivers flow more slowly, or not at all. Irrigation systems calibrated for 1 gram no longer function correctly. Infrastructure tells the same story. Every building, bridge, dam, road, and pipe system on Earth has been designed with Earth's gravitational acceleration as a fundamental parameter. The structural calculations for a skyscraper assume 1 gram. The flow rates in a water distribution system assume 1 gram. The drainage slopes of roads and runways assume 1 gram. The depth of foundations assumes 1 gram, acting on the weight of the structure above. Change gravity, even slightly, even gradually, and every piece of engineered infrastructure on Earth becomes miscalibrated. Not immediately dangerous, perhaps, but increasingly unreliable and unpredictable as the gravitational environment diverges from the design assumption. There is something almost poetic about the comprehensiveness of this. We did not design our world for 1 gram because we were careful. We designed it for 1 gram because we had no choice. We exist in a 1 gram environment. We build in a 1 gram environment. We evolved in the 1 gram environment. And every tool and institution we have ever created reflects this. The gravitational constant G is embedded in our civilization so thoroughly that you cannot pull it out without the civilization coming apart with it. It is not a variable in our engineering equations. It is the environment in which all engineering takes place. The same is true at the level of chemistry and physics. Many chemical processes that occur naturally on Earth depend on gravity for the separation of phases, the settling of denser materials to the bottom, and the rising of lighter materials to the top. Sedimentation in rivers, the formation of geological layers, the separation of oil from water, the behavior of fermentation in brewing and baking, all of these depend on the gravitational separation of materials by density. In microgravity, mixtures that would separate into layers on Earth remain mixed. Emulsions that would separate remain stable. Precipitates that would settle remain suspended. The chemistry of Earth's surface, both the natural chemistry and the industrial chemistry, would change in a world of reduced gravity. Combustion is another example. Fire on Earth burns upward because hot combustion products, carbon dioxide, water vapor, nitrogen, are less dense than the surrounding air, and gravity causes them to rise, drawing fresh, oxygen-rich air in from below. This convective current is what gives a candle flame its characteristic teardrop shape. In microgravity, there is no convection. Fire in the absence of gravity burns as a small sphere, because without the density-driven convection, combustion products surround the flame, and fresh oxygen can only reach it by diffusion, which is slow. The flame dies out quickly without a forced air supply. Engines that rely on convection to cool themselves or to deliver fuel would behave differently. Internal combustion engines, which are far less sensitive to gravity than open flames, would continue to function, but many industrial processes that rely on convective heat transfer would need to be redesigned. I want to spend a moment on the question of the Moon, because the Moon's role in Earth's habitability is profound and poorly understood by most people, and because it is entirely gravity dependent. The Moon's gravitational influence on Earth produces tides, not just the ocean tides that sailors and coastal dwellers are familiar with, but tides in the solid rock of Earth's crust, in the atmosphere, trochs, and historically in the liquid interior of the early Earth. The tidal dissipation of energy, the friction generated by the tidal distortion of Earth's rock as the Earth rotates under the Moon's gravitational pull, is slowly transferring angular momentum from Earth's rotation to the Moon's orbit. The Moon is receding from Earth at a rate of about 3.8 centimeters per year. Earth's rotation is slowing at a corresponding rate. A day on Earth is getting slightly longer each century. 4 billion years ago, a day on Earth was roughly 6 hours long. The Moon was much closer, and its tidal influence was much stronger. This tidal influence on the early Earth may have been crucial for the origin of life. The tidal cycles on the early Earth would have been dramatic, tides many times higher than current ocean tides, occurring far more frequently due to the shorter day. Coastal regions would have experienced rapid cycles of flooding and drying, creating the kind of concentrated, cyclically changing mechanical environment that some origin of life theories require. The tidal heating of the early Earth may have contributed to maintaining the planet in a partially molten state for longer than it would otherwise have been, affecting the chemistry of the early mantle and crust. Gravity, in the form of the Moon's tidal gravitational influence on Earth, may have been part of the story of how life began. Remove Earth's gravity, and the Moon's orbit is not immediately affected. The Moon is in orbit around Earth because of Earth's gravity. But if Earth's gravity were removed, the Moon would continue moving in whatever direction it was heading at the moment of removal at its orbital speed of about 1 kilometer per second, and would head off into the solar system on a new trajectory. The Moon would not fall toward Earth, it would leave. the loss of the moon's gravitational influence on Earth would remove the primary cause of ocean tides, an effect that, while not immediately catastrophic, has been woven into the ecology of coastal and intertidal zones for hundreds of millions of years and is embedded in the life cycles of countless species. The stabilization of Earth's axial tilt by the moon is perhaps more important than the tides. Earth's current axial tilt of about 23.5 degrees, which is responsible for the seasons, the variation in the length of days, and the distribution of sunlight across latitudes, is remarkably stable over timescales relevant to the evolution of complex life. It varies only slightly over timescales of tens of thousands of years, driven by gravitational perturbations from other planets, in cycles that are too slow to disrupt the fundamental habitability of the planet. Without the moon's stabilizing influence, Earth's axial tilt would vary chaotically between near zero and very high values over timescales of millions of years, the same way Mars's tilt varies, because Mars lacks a large moon. This axial variation would drive climate swings far beyond anything that has occurred in Earth's history, potentially freezing and baking different parts of the planet repeatedly in ways that would make the sustained development of complex life much more difficult. Gravity binds these systems together. The moon's gravitational interaction with Earth stabilizes the axial tilt. The stabilized axial tilt allows a stable climate. The stable climate allows the uninterrupted evolution of complex life over billions of years. Remove gravity from Earth, and you don't just remove the Earth's own gravitational field. You remove the entire gravitational relationship between Earth and Moon, between Earth and Sun, between Earth and the rest of the solar system. You remove the tides. You remove the axial stabilization. You remove all the consequences of those things that have been accumulating for 4.5 billion years. The Earth without gravity would not be the Earth. It would be the material that was the Earth before gravity assembled it into the thing we inhabit. Now, I want to take this further because the thought experiment becomes even more revealing when you compare Earth's gravitational environment to other bodies in the solar system. The comparison shows you not just what happens when gravity disappears, but what happens when gravity is different, and those real comparisons give us observational data, not speculation. The Moon has about 16% of Earth's surface gravity, 1.62 meters per second squared, compared to Earth's 9.8. It has no atmosphere worth measuring. Its surface pressure is so low, about 10,012 pascals, compared to Earth's 1,000 and 1,325, that it is classified as an exosphere, a region so thin that the molecules in it almost never collide with each other. The Moon cannot hold an atmosphere because its gravity is too weak to retain the gas molecules against the speed of their thermal motion. At the temperatures on the Moon's surface, gas molecules move fast enough that they simply escape into space faster than any volcanic outgassing or comet impact can replenish them. The Moon's weak gravity means no atmosphere, which means no weather, which means no erosion of the kind that on Earth continuously resurfaces and reshapes the landscape. The Moon's surface looks the way it does, covered in ancient craters that have persisted for billions of years, because without an atmosphere and without liquid water, nothing wears anything down. The Moon is a record of its early history, preserved because gravity was not strong enough to hold the tools of erosion. Mars has about 38% of Earth's gravity, 3.72 meters per second squared. Mars has an atmosphere, but a thin one. The surface pressure on Mars is about 0.6% of Earth's surface pressure, roughly equivalent to Earth's atmosphere at an altitude of 35 kilometers. You would suffocate immediately on Mars's surface, even in the highest pressure regions, and the pressure is so low that liquid water cannot exist there. It would instantly boil away. Mars once had liquid water. We know this from the geological record. Ancient river channels, lake beds, delta formations. Mars once had a thicker atmosphere that could sustain liquid water. What happened? Mars's gravity was strong enough to hold an atmosphere initially, but Mars lost its global magnetic field early in its history, probably within the first 500 million years, and without a magnetic field to deflect the solar wind. The solar wind gradually stripped away the upper atmosphere over billions of years, reducing Mars from a world that might have been habitable to the cold, thin, dry place it is today. Mars's gravity was enough to hold a primitive atmosphere. It was not enough to hold it against the erosion of the solar wind once the magnetic shield was gone. Venus, by contrast, has about 91% of Earth's gravity, 8.87 meters per second squared, and has retained a massive atmosphere. Venus's surface pressure is about 92 times Earth's, equivalent to the pressure at about 900 meters depth in Earth's oceans. Its atmosphere is almost entirely carbon dioxide, producing an extreme greenhouse effect that drives surface temperatures to about 465 degrees Celsius, hot enough to melt lead. Venus's gravity was strong enough to retain its atmosphere even without a global magnetic field. The solar wind strips the upper layers of Venus's atmosphere, but Venus's gravity is strong enough that the atmosphere is continuously replenished from the dense lower layers faster than a solar wind can remove it. Venus is a demonstration of what happens when you have near-Earth gravity, but a different initial chemistry, a massive atmosphere, runaway greenhouse warming, a surface hostile to any life as we know it. These three bodies, Moon, Mars, Venus, at gravities of 16, 38, and 91% of Earth's, show you a spectrum of outcomes. At 16%, no atmosphere, no liquid water, no ridge ocean, no weather, a sterile record of ancient bombardment. At 38%, a thin atmosphere barely held against the solar wind, no liquid water on the surface, a world that may once have been habitable but lost the conditions before life had time to take hold and persist. At 91%, a massive atmosphere, catastrophic greenhouse warming, a surface that would immediately kill any Earth life. Earth at 100% sits in a narrow range where gravity is strong enough to hold a substantial atmosphere with the right composition, strong enough to keep liquid water on the surface, strong enough to maintain the water cycle and the carbon cycle, but not so strong that it crushes the biosphere into a different configuration. The numbers here are striking. The habitable range for gravity, the range where a rocky planet at Earth's distance from the Sun has the conditions for liquid water, an atmosphere, and the possibility of complex life, is probably not very wide. Too much less than Earth's gravity, and you lose the atmosphere and the water. Too much more, and you may have a different kind of problem. A planet that holds gases too well, accumulating a hydrogen and helium atmosphere from the solar nebula, and never developing a rocky surface plus ocean configuration. Jupiter and Saturn, with their enormous gravities, are dominated by hydrogen and helium because their gravity was strong enough to accrete the lightest gases directly from the solar nebula. Earth's gravity was not strong enough for that. The solar wind stripped the lightest gases from the early Earth, leaving the heavier gases like nitrogen and carbon dioxide that form the basis of Earth's current atmosphere. Gravity calibrated the atmospheric composition. The specific value of G matters. Now, let me push into the biology more deeply, because the relationship between gravity and life is not just architectural, it runs all the way down to the cellular level. But before we go there, I want to address something that almost never gets addressed in discussions of this topic: the relationship between gravity and the other fundamental forces. Because understanding why gravity is uniquely important and uniquely different from the other forces is essential to understanding why you cannot simply turn it off and keep everything else running. Physics currently recognizes 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The strong force holds atomic nuclei together. The weak force governs certain types of radioactive decay and is responsible for the nuclear reactions that power the sun. Electromagnetism governs the interaction of charged particles and is responsible for essentially all of chemistry, all of light, and all of the electromagnetic phenomena that make modern technology possible. Gravity governs the interaction of masses. Of these 4 forces, gravity is by far the weakest. This sounds paradoxical. Gravity is the force we experience most directly and continuously in everyday life, and it shapes the largest structures in the universe. How can it be the weakest? The answer is that gravity is weak in the sense that the gravitational force between any 2 individual particles is extraordinarily small compared to the electromagnetic force between the same particles. The electromagnetic force between an electron and a proton, which is what holds atoms together, is about 10 followed by 36 zeros. A number so large it essentially means gravity is irrelevant at the scale of individual particles. Gravity only becomes dominant at large scales because it is always attractive and has infinite range, while electromagnetism has both attractive and repulsive variants that cancel out at large scales. Matter in the universe is electrically neutral on large scales. Positive and negative charges cancel each other, so there is no large-scale electromagnetic force between distant objects. But all mass is positive, there is no negative mass, so gravity always attracts and never cancels. Add enough mass together, and gravity accumulates into something that dominates all other forces at that scale. Which is why, at the scale of planets, stars, and galaxies, gravity rules, despite being the weakest force at the particle scale. This asymmetry has a profound consequence for the thought experiment. The other fundamental forces are genuinely switchable, in the sense that you can shield them. You can block electromagnetic radiation with a Faraday cage. You can shield against charged particles with appropriate materials. You cannot shield against gravity. There is no known gravitationally neutral material. Everything with mass is affected by gravity. The only way to remove gravity from a region is to remove all the mass that is generating it. And mass, unlike electric charge, comes in only one sign. You cannot cancel it. This is why losing gravity is not like losing electricity or losing light. It is not a technological failure. It is not a malfunction in a system that can be repaired. It would require a change in the fundamental structure of space-time itself, a change in the relationship between mass and the geometry of space. No mechanism for such a change is known to physics. The thought experiment requires a premise that is not just technologically impossible, but physically undefined. And yet, the thought experiment is worth running, not because the premise is plausible, but because following it reveals the architecture of the real world. When you ask what does the world look like without gravity, you're asking, what does gravity contribute to the world? And the answer, as we have been building piece by piece, is everything. Everything that is not governed by chemistry and particle physics alone. Every structure larger than a molecule. Every planet. Every star. Every ocean. Every atmosphere. Every geological cycle. Every biological adaptation above the cellular level. Every piece of engineering humanity has ever built. The four fundamental forces divide responsibility for reality as follows. Roughly, the strong force holds atomic nuclei together. Without it, the flying force, atoms dissolve into individual protons. And some of it is a low body. Electromagnetism holds electrons to nuclei and holds atoms together into molecules and holds molecules together into materials. Without it, chemistry ceases and matter becomes a gas of individual protons, neutrons, and electrons. Gravity holds everything together above the molecular scale. Without it, the organized structures of the universe above the size of a molecule cease to exist. The weak force regulates the nuclear reactions that power stars. Without it, stars do not burn, heavy elements do not form, and the universe remains a sea of hydrogen and helium with nothing heavier. Each force is responsible for a specific scale and type of organization in the universe. Remove any one of them, and the universe becomes less organized, less complex, less interesting. Remove gravity, and you remove the scale at which the universe has produced planets, stars, galaxies, and everything that depends on them, including life. One more comparison that clarifies the stakes. Imagine a universe identical to ours in every respect, except that the gravitational constant G, the fundamental constant that determines the strength of gravity, were 10 times smaller. Not 0, just 1/10 of its current value. What would such a universe look like? The immediate consequence would be that the minimum mass required to ignite nuclear fusion to form a star would be much lower, because a lower gravitational constant means less compressive pressure at the center of a protostellar cloud, and therefore a smaller cloud mass can achieve the temperatures and pressures required for fusion. Stars would be smaller, less energetic, and shorter lived. The most massive stars, which in our universe can be hundreds of times the mass of the Sun, would be rarer or absent. The smallest stars, red dwarfs, would be the same or similar. The range of stellar masses would be compressed toward the lower end. More importantly, the rate of heavy element production would change. Heavy elements are produced in the interiors of massive stars and scattered by supernova explosions. Smaller, less massive stars produce fewer heavy elements and die differently. They do not explode as supernovae in the same way. A universe with a smaller gravitational constant would have less vigorous supernovae and a different rate of heavy element enrichment. Carbon, oxygen, nitrogen, iron, silicon, the elements of planetary geology and biochemistry, would be produced at different rates and in different abundances. The universe might have planets, but those planets would have different chemical compositions. Whether those different compositions would support life is genuinely unclear. Conversely, a gravitational constant 10 times larger would produce more massive stars that burn faster and die sooner, shortening the window of time during which planets around those stars could develop and sustain life. Planets would be more massive, with higher surface gravities, potentially making the development of land life more difficult. The universe would be organized differently at every scale. The gravitational constant that exists in our universe appears, when you run these calculations, to be in a range that allows for long-lived stable stars, for the production of heavy elements, for the formation of rocky planets in stable orbits, and for the development of complex life. Whether this appearance of fine-tuning reflects something deep about the nature of reality, the anthropic principle, the multiverse, the selection effects of conscious observation, is a philosophical question that physics cannot currently answer. But the sensitivity of the outcome to the value of the gravitational constant is real and measurable, and it underlies the significance of any thought experiment about gravity changing. Every cell in your body exists in 1 gram. Not just your skeleton and muscles, every cell, including the neurons in your brain, the cells lining your gut, the red blood cells in your bloodstream. And every one of these cells has been shaped by evolution, occurring in 1 gram over hundreds of millions of years. The question of which specific features of cell biology are adaptations to gravity versus which would be exactly the same in a zero-gravity environment is an active area of research. But some answers are already clear. The cytoskeleton, the internal scaffolding of the cell, made of protein filaments that give cells their shape and allow them to move and divide, is sensitive to mechanical forces. In a gravitational environment, cells experience compression and tension from the weight of overlying tissues. The cytoskeleton responds to these forces by reorganizing, a process called mechanotransduction. Cells in a gravitational environment are constantly translating mechanical signals into biochemical ones, regulating gene expression, cell division, and cell differentiation based on the mechanical forces they experience. In microgravity, this signal changes, and cells respond by changing their behavior. Stem cells in microgravity differentiate differently than they do in 1 gram. Immune cells in microgravity show altered function, reduced proliferation, reduced cytokine production, changes in the expression of surface proteins. Cancer cells in microgravity show different growth patterns. Every cell type that has been studied in microgravity shows some measurable change in behavior compared to 1 gram. The implications of this are significant for the thought experiment. If Earth's gravity changed, if it weakened significantly over a period of weeks or months, every cell in every organism on Earth would begin receiving different mechanical signals. Those signals regulate gene expression. Changed gene expression means changed protein production. Changed protein production means changed cell behavior. Changed cell behavior across every cell in every organism means changed organismal function. The changes would not be immediately catastrophic. For most cell types, cells can tolerate a range of mechanical environments, but they would be real and measurable. Over months and years, the effects would accumulate. Organisms that are finely calibrated to 1 gram, which is every multicellular organism on Earth, would begin to malfunction in ways they were not evolutionarily equipped to handle. There is a more fundamental connection between gravity and life that operates at the evolutionary level. Life on Earth has been evolving in 1 gram for approximately 3.7 billion years. The first cells had to deal with gravity. They existed in water, so the buoyancy of water partially offset gravity. But the gravitational sorting of materials, the direction of nutrient gradients, the settling of particles, the direction of light, all of these were gravity influenced. As life became more complex and eventually left the water to colonize land, the gravitational challenge intensified. Moving on land requires structural support against the gravitational force, energy expenditure to lift the body, and sophisticated proprioception, the sense of body position and space, calibrated to 1 gram. The diversity of solutions that evolution has produced for the challenge of living in 1 gram is extraordinary. Plants grow upward against gravity toward the light, using turgor pressure and cell wall rigidity to maintain structure. Trees, which can grow to over 100 meters tall, as in the case of the coast redwood, solve the problem of lifting water from roots to leaves through a combination of osmotic pressure, capillary action, and the tension created by evaporation from leaf surfaces, all of which operate against gravity. The tallest trees in the world are, in a sense, experiments in how high you can pump water against gravity using biological mechanisms. The answer, it appears, is about 130 meters. Beyond that, the tension in the water column exceeds the cohesive strength of liquid water and the system fails. Animals have solved the gravity challenge through skeletons, either internal skeletons made of bone or cartilage, as invertebrates, or external skeletons made of chitin or other materials, as in arthropods. The design of these skeletons is a gravitational engineering problem. The cross-sectional area required to support a bone under compression scales with body mass, and body mass scales with the cube of body length, while cross-sectional area scales with the square of body length. This means that as you scale an animal up in size, the bones must become disproportionately thicker relative to body length to support the increased weight. This is why an elephant, scaled up to the size of a building, would need legs so thick relative to its body that it couldn't move. The engineering fails at some point. The largest land animals that have ever existed, certain sauropod dinosaurs, possibly reaching 70 to 80 tons in mass, were at or near the biological limit for body mass in Earth's 1 gram environment. In a lower gravity environment, much larger land animals would be possible. In a higher gravity environment, the maximum body size for mobile land animals would be smaller. The connection between gravity and the evolution of the nervous system is one of the most intriguing and least discussed aspects of this relationship. The vestibular system, the gravity-sensing apparatus of the inner ear, is one of the most ancient sensory systems in vertebrate evolution. The otolith organs, which detect linear acceleration, including gravitational acceleration, are present in all vertebrates and in many invertebrates. The semicircular canals, which detect angular acceleration, rotation, are also ancient and are present in essentially all vertebrates. These gravity-sensing systems are not just useful for orientation and balance. They are deeply integrated into the neural circuits that control movement, posture, gaze stability, and spatial cognition. The development of spatial cognition, the ability to form mental maps of the environment, to navigate, to reason about the positions of objects in three-dimensional space, may have been driven in part by the demands of living in a gravitational environment. Knowing which way is down is the most fundamental form of spatial information available to any organism. It is the reference axis against which all other spatial information is organized. The cognitive architecture of spatial reasoning in vertebrates, including humans, is built around the gravitational vertical as a primary reference. Change the gravitational environment, and you change the primary reference axis of spatial cognition, which disrupts far more than just balance. This is why astronauts in microgravity consistently report spatial disorientation as one of the most challenging aspects of the experience. The vestibular system is receiving signals that are inconsistent with its evolutionary and developmental calibration. The visual system, the proprioceptive system, and the vestibular system normally provide consistent information about gravitational vertical and are heavily cross-referenced by the brain. In microgravity, they provide inconsistent information. The vestibular system reports the absence of a gravitational acceleration vector, while the vagal system in proprioception may report familiar environments and body orientations. This sensory conflict produces disorientation, nausea, and the condition known as space adaptation syndrome, which affects the majority of astronauts in the early days of a microgravity mission. The brain adapts, usually within a few days to a week, by essentially recalibrating its integration of vestibular signals. But the adaptation is to the new environment, not a fix to the underlying conflict. When astronauts return to Earth, they must readapt again. The human brain, evolved over millions of years in 1 gram, is specifically constructed to handle 1 gram. It is not a general-purpose spatial reasoner that happens to have found itself in a 1 gram environment. It is a 1 gram spatial reasoner specialized for the gravitational environment it evolved in. Change that environment, and you change the performance characteristics of the most complex object in the known universe. All of this, the biology, the evolution, the neuroscience, points to the same conclusion that the physical analysis does, but from a different direction. Gravity is not an external condition that life adapted to. Gravity is the condition in which life formed, the condition through which life evolved, and the condition that life's every feature reflects. The living world is not in a gravitational environment. The living world is a gravitational environment, an organized, self-sustaining expression of what chemistry does when you give it 4.5 billion years of evolution in 1 gram. One more layer to this: the chemical and geological cycles that make Earth habitable over geological timescales are gravity dependent at every step. But before we go there, let me spend time on something that is easy to overlook because it is so obvious: the relationship between gravity and human civilization specifically. Not life in general, not biology in the abstract. The specific, particular, historically contingent civilization that you and I are part of. Human civilization began in river valleys. The Tigris and Euphrates, the Nile, the Indus, the Yellow River. These are not coincidental locations for the first cities. They are places where gravity delivers water from mountains to plains, deposits silt that enriches the soil, and provides a reliable, predictable, renewable supply of the one resource that agriculture requires above all others. The entire agricultural revolution, the transition from hunting and gathering to farming, that made civilization possible, was a project in harnessing gravity. Farmers do not fight gravity, they direct it. They build irrigation channels that use gravity to move water from rivers to fields. They terrace hillsides to slow the gravitational movement of water and soil. They plant on slopes oriented to receive sunlight using the geometry of the landscape shaped by gravitational erosion. The earliest civilizations were gravity management projects. The wheel, one of the most consequential inventions in human history, is a gravity machine. It reduces the friction of moving objects over a surface, allowing a smaller gravitational force, a person pushing, to move a much larger weight against gravity's tendency to resist that movement. Carts, ploughs, millstones, pottery wheels, water wheels, all of these are applications of the same principle, using mechanical advantage to redirect gravitational forces into useful work. The Industrial Revolution, which dramatically accelerated the pace of human civilization, beginning in the 18th century, was powered initially by water wheels and steam engines, both of which are gravity machines. Water wheels capture the kinetic energy of falling water, which falls because gravity accelerates it. Steam engines, in their earliest configurations, lifted water from coal mines using atmospheric pressure, the weight of the atmosphere pressing down on a piston from which steam had been condensed, creating a vacuum. James Watt's improvements to the steam engine made it a more general-purpose machine. But the thermodynamic cycle of the steam engine is still fundamentally a process of heating and cooling that exploits density differences, which are gravitational in the sense that gravity is what makes density differences dynamically significant. Transportation has always been a negotiation with gravity. Roads and railways are engineered to manage slopes, to find routes that minimize the energy required to move against gravity and maximize the energy recovered from moving with it. The difference in elevation between 2 points on a trade route is a gravitational cost that has shaped the development of cities, the roots of empires, and the outcomes of wars. Mountain passes that allowed gravity-assisted descent on one side and manageable ascent on the other became choke points of history. Rivers that could be navigated downstream with the assistance of gravity, and eventually upstream against it with the development of locks and canals, were arteries of trade and communication. Finding the geography of human civilization is gravitational geography. Architecture is a sustained conversation with gravity. Every building is a structure that uses the compressive strength of its materials to resist the gravitational force trying to collapse it. The physics of a stone arch, which uses the weight of the stones pressing down on each other to create a structure that can span a gap without any single stone bearing tensile load, is a gravitational engineering insight that was independently discovered by ancient cultures on multiple continents. The Gothic cathedral's flying buttresses transfer the lateral thrust of the stone vault to external piers, a gravitational engineering solution to the problem of a heavy stone ceiling trying to push the walls outward. The steel-framed skyscraper's core carries the entire gravitational load of dozens of floors through a rigid central structure to the foundations. Every architectural innovation in history has been, in part, a new answer to the question, how do we manage gravity while achieving the space and span we need? Material science, the study of how materials behave under load, is fundamentally a study of gravity's consequences. The properties we care most about in structural materials are their behavior under gravitational loading, compressive strength, tensile strength, stiffness, resistance to fatigue under repeated loading. Concrete is strong in compression, which is what gravity produces in columns and arches, but weak in tension. Steel is strong in both compression and tension, which is why steel-reinforced concrete can span much greater distances than plain concrete. The development of new materials over human history has repeatedly been driven by the need to build taller, span wider, carry more weight, all of which are responses to gravity. The energy systems that power modern civilization are all gravity adjacent. Hydroelectric power, which generates about 16% of global electricity, is direct gravitational energy conversion. Water falls from a high reservoir to a low one, turning turbines on the way down. The stored energy in a hydroelectric reservoir is essentially gravitational potential energy, the energy of the water sitting at a height from which it can fall. Coal, oil, and natural gas are fossil fuels. The chemical energy stored in the biological molecules of organisms that lived hundreds of millions of years ago, whose dead bodies sank to the bottom of ancient seas and lakes under gravity. Were buried by gravitational sedimentation, were compressed by the weight of overlying sediments into hydrocarbons, and were then trapped by geological formations shaped by gravitational tectonics. The fuel that powered the Industrial Revolution and continues to power most of global civilization is, in a very literal sense, compressed and chemically transformed gravity, the product of billions of years of gravitational processes acting on biological material. Nuclear power uses the energy released by nuclear fission, the splitting of heavy atomic nuclei like uranium-235. But why does uranium-235 exist? Because it was synthesized in the interior of massive stars in the final moments before those stars underwent core collapse supernovae. The synthesis of elements heavier than iron requires a neutron-rich environment with extremely high temperatures and densities, conditions that exist in the collapsing core of a massive star in the last seconds of its life. And in the neutron-star merger events that also produce heavy elements. The energy released in these cataclysmic events disperses the heavy elements into the interstellar medium, where they eventually become incorporated into new planetary systems, including ours. The uranium in Earth's crust was made in stellar catastrophes driven by gravity. The nuclear power plants that use that uranium are, at the deepest level, delayed gravitational energy, stellar gravitational energy released eons ago, stored in atomic nuclei, and finally converted to electricity by humans in the 21st century. Even the digital economy that characterizes the most advanced contemporary civilizations is gravitationally embedded, though it takes a moment to see this. Data centers, the physical infrastructure of the internet, cloud computing, and digital communication, require enormous amounts of electricity, which comes primarily from the gravity-dependent energy sources described above. The semiconductor chips that perform computation are manufactured in clean room facilities that are extraordinarily sensitive to vibration, including the micro-vibrations caused by ground motion from traffic and mechanical equipment nearby. The precision required to manufacture modern chips, with features measured in a few nanometers, requires isolation from the gravitational disturbances of the ordinary physical world. And the satellites that relay digital communication around the globe, the GPS satellites that tell your phone where it is, the communication satellites that route international internet traffic, the Earth observation satellites that monitor weather and agriculture and sea level, all of them are in orbit because of precise gravitational calculations. They are where they are because of very careful management of the gravitational interaction between the satellite and Earth. Every single thing that human beings have built, from the first grain storage pit in a Neolithic village to the International Space Station, reflects and responds to gravity. Our engineering is gravity engineering. Our energy is gravity energy. Our transportation is gravity navigation. Our architecture is gravity architecture. Our civilization is a gravity civilization, a particular, historically contingent answer to the question of what intelligent organisms can build when they have 9.8 meters per second squared to work with and 10,000 years to figure out how. Remove gravity, and the answer to that question becomes incoherent. Not just the buildings fall, not just the water runs away. The entire body of knowledge, technique, and institutional memory that constitutes human civilization, calibrated to 1 gram, designed for 1 gram, tested in 1 gram, becomes inapplicable. We would not know how to rebuild, not because we are not intelligent, because the intelligence we have developed is intelligence for this gravitational environment. It is not a general purpose intelligence that could immediately adapt to a fundamentally different physical environment. It is an intelligence grown in 1 gram for 1 gram out of 4.5 billion years of evolutionary and 10,000 years of cultural experience in 1 gram. This is the most profound version of the answer to the question, what would happen if Earth lost gravity? It is not the disaster sequence, though that is dramatic and real. It is this: we would not know what to do. Not because we are helpless, because the knowledge of what to do, the accumulated wisdom of human civilization, is knowledge about how to live in this gravitational world. Without this gravitational world, that knowledge has no referent. It is answers to questions that no longer exist. There is a related point that deserves to be made explicitly. The experience of weightlessness, which is the closest thing to lost gravity that any human has actually experienced, is profoundly disorienting in ways that go beyond the physiological. Astronauts who have spent months on the International Space Station described a cognitive and perceptual reorientation that persists throughout the mission. The sense of up and down, which feels so natural and automatic on Earth that we barely notice it, does not exist in microgravity in the same form. There is no gravitational vertical. Every direction is equally down, in the sense that there is no force preferentially pointing in any direction. Astronauts adapt to this by using visual cues. They orient themselves relative to the walls and ceilings of the space station, which are labelled and colour-coded to provide a substitute for the gravitational vertical. But the adaptation is cognitive, not perceptual. The vestibular system is still not receiving the signal it expects. The unconscious, automatic sense of orientation that every Earth-born human being takes completely for granted is simply absent. This absence, this small, local, temporary loss of gravitational orientation in a carefully designed and controlled environment with 6 highly trained crew members, produces measurable cognitive effects, physiological disruption, and a perceptual reorganization that takes days to adapt to and days more to reverse upon return to Earth. Scale that up, not to a space station with 6 people, but to the entire surface of a planet with 8 billion. Not for 6 months, but permanently. Not with the safety net of eventual return to a gravitational environment, but with no return possible. The cognitive and perceptual disruption alone would be catastrophic before the atmospheric and oceanic and geological consequences had time to kill anyone. The human brain, the human body, human civilization, all of it is a gravitational artifact. We are made of the same atoms as everything else in the universe, but those atoms are organized in us by a history that gravity wrote. The organization, the specific, contingent, extraordinary arrangement of matter that constitutes a living, thinking, building, wondering human being, is the product of 13.8 billion years of a universe in which gravity was always present, always shaping, always sorting matter from the simple into the complex. You are gravity's autobiography, written in carbon and water and electrical signals, expressed in consciousness and culture and the accumulated knowledge of 10,000 years of civilization, but gravity's autobiography nonetheless. The universe used gravity to organize itself into something that could ask the question, what would happen if gravity disappeared? And the answer to that question is everything that made it possible to ask the question would cease to exist. That is either a deeply uncomfortable thought or a deeply beautiful one, depending on how you hold it. I find it both. The next time you stand up from a chair, the next time you feel the ordinary, unremarkable, utterly reliable pressure of the floor against your feet, you might pause for a moment and recognize that pressure for what it is. Not a constraint, not a force keeping you down, a history, an organization, a 4.5 billion year project in which the universe took hydrogen and object pages, made the air you're breathing and the water in your body, and the iron in your blood and the calcium in your bones, made the sun that warms the planet and the moon that stabilizes its tilt, and the tides that may have been part of the chemistry that started life, made the entire geological and biological and civilizational story that led, step by step, gravitational step by gravitational step, to this moment and this question, made you curious enough to ask it. That is what gravity is. That is what you take for granted every moment of every day. And that, all of that, is what you would lose. The rock cycle, the process by which rock is formed, weathered, transported, deposited, buried, metamorphosed, and eventually returned to the surface through volcanic activity, is driven by gravity at every stage. Rain falls because gravity pulls water from the atmosphere. Rivers flow because gravity pulls water toward lower elevations. Sediment is transported downstream because gravity keeps the moving water flowing and carries suspended particles along with it. Sediment is deposited in deltas and ocean basins because gravity settles particles out of the water column when the water slows. The deposited sediment is buried and compressed by the weight of overlying sediments, a gravitational process. The buried rock is eventually subducted under tectonic plates and returned to the mantle, a process driven partly by the density difference between oceanic and continental crust, which is a gravitational effect. The mantle material melts and rises through volcanic conduits because it is less dense than the surrounding mantle, a buoyancy effect that is gravity dependent. The volcanic rock erupted at the surface, weathers, and the cycle begins again. Every link in the rock cycle is a gravitational link. Remove gravity and the rock cycle stops. The surface of Earth would no longer be continuously resurfaced and chemically processed. The carbon, phosphorus, nitrogen, and sulfur cycles, which depend on the rock cycle to recycle nutrients from the deep Earth back to the surface, would stop. The slow geochemical exchange between the surface and the deep Earth, which has regulated the composition of the atmosphere and oceans over billions of years and is responsible for keeping the planet habitable despite a brightening sun and changing external conditions, would stop. The sun has brightened by about 30% since Earth formed 4.5 billion years ago. The early Earth, receiving 30% less solar energy than today, should have been completely frozen. The faint young sun paradox. It was not completely frozen, based on geological evidence of liquid water 3.8 billion years ago. The explanation involves higher concentrations of greenhouse gases in the early atmosphere, particularly carbon dioxide and methane, which compensated for the lower solar energy input. As the sun brightened over billions of years, the concentration of greenhouse gases declined, drawn down by weathering of silicate rocks and deposition of carbonate rocks. The geochemical process governed by the rock cycle, maintaining the surface temperature within a habitable range. The thermostat that kept Earth habitable as the sun brightened is the carbon-silicate cycle. The carbon-silicate cycle runs on gravity. Remove gravity, and the thermostat stops working. Earth's surface temperature would become hostage to the full variability of solar output, with no geochemical buffering to compensate. This is what it means to say that gravity is the architect of habitability, not just of the current conditions on Earth, but of the long-term stability of those conditions. Not just of the starting state, but of the maintenance process that has kept the starting state approximately intact for 4.5 billion years, despite a brightening sun, comet and asteroid bombardments, massive volcanic eruptions, and the evolution of an entirely new kind of chemistry, life, that has itself dramatically changed the composition of the atmosphere. Earth has remained habitable for 4.5 billion years because gravity has been running the maintenance systems, the rock cycle, the water cycle, the carbon cycle, the tectonic system, continuously for that entire time. Remove gravity, and the maintenance systems stop. Not immediately, not catastrophically in the first moment, but inexorably, over months and years and decades, the conditions drift away from the narrow range that makes complex life possible, and they do not come back. There is no restoring force. The restoring force was gravity. Here is the thing I want to leave you with, because this thought experiment has a purpose beyond the disaster sequence it describes. Every time we ask, what would happen if X were removed from the world, we are, in some sense, asking, what does X do? The gravity thought experiment works because gravity does so many things simultaneously and so thoroughly that removing it forces us to confront all of them at once. It makes visible what is normally invisible, the comprehensive, structural, foundational role that gravity plays in making Earth what it is. The oceans are there because gravity holds them. The atmosphere is there because gravity holds it. The planet is the shape it is because gravity shaped it. The chemistry of the crust is what it is because gravity sorted it. The moon is where it is because gravity put it there and keeps it there. The tides exist because of the moon's gravity. Life evolved in 1 gram because that is the only gravitational environment that existed for it to evolve in. Your bones are the shape they are because gravity loaded them for your entire life. The buildings you live in were designed for gravity. The water system that supplies your water was designed for gravity. The roads you drive on were graded for gravity. Every human institution, every piece of infrastructure, every biological system, every geological feature, all of it reflects the specific gravitational environment in which it exists. You cannot remove the architect and keep the building. The building is the architect's work, accumulated over 4.5 billion years, in the specific gravitational field that Earth has always had. The building is, in a very real sense, gravity, given structure, given chemistry, given biology, given civilization. We take gravity for granted because it has never changed, not in all of human history, not in all of evolutionary history, not in the entire 4.5 billion year history of Earth. The gravitational acceleration at Earth's surface has been approximately 9.8 meters per second squared for as long as there has been an Earth surface. Every living thing that has ever existed on this planet has lived its entire life in that field. Every rock has been shaped by it. Every ocean has been held by it. Every breath of air has been kept here by it. We don't notice the thing that never changes. We notice what changes. Gravity never changes, and so we never notice it until we ask what the world would look like without it. And then we see for the first time that the world is not in a gravitational field the way a fish is in water. The world is the gravitational field made manifest. The world is what gravity does, given 4.5 billion years and the right raw materials. The question, what would happen if Earth lost gravity, has a simple answer and a profound one. The simple answer is everything would fall apart. The profound answer is there would be no everything to fall apart, because the everything we are describing was made by gravity in the first place. The question is self-defeating. You cannot remove gravity from Earth without removing the Earth, because the Earth is what gravity has been doing for 4.5 billion years. That is not a trick of language. It is the deepest truth the thought experiment reveals. The universe, at every scale above the atomic nucleus, is organized by gravity. Atoms form molecules through electromagnetic forces. Molecules form cells and rocks and water through chemical forces. But cells form organisms. Organisms form ecosystems. Ecosystems form planets. Planets form solar systems. Solar systems form galaxies. And galaxies form the large-scale structure of the universe. All of this happens through gravity. Remove it, and you remove the organizing principle of everything larger than a molecule. What remains is the raw material, the atoms and molecules, but not the structure, not the architecture, not the world. Without gravity, the universe would not be as fascinating. It is due to the effects of gravity that matter coalesces into planets and stars. There would be no stars, no creation of heavy elements by stars, and no creation of planets from those heavy elements. Without the gravitational force of planets, planets do not have the ability to create chemical compounds needed to sustain or develop life. Without gravity, life cannot persist or evolve on timescales long enough to develop intelligence. If there were no gravitational force acting on atoms of the universe, they would remain in constant motion and not cluster together, creating the shape of stars and planets. The universe without gravity would consist of only hydrogen and helium. There would be no features whatsoever, only an endless cloud of hydrogen and helium. Your environment is composed of more than just a gravitational field. You are part of and created by gravity. Atoms in your body are composed of materials created in stars, producing that star's energy through the force of gravity. The energetic products of those stars broke apart from an explosion, but were once again drawn back together because of the effects of gravity. Your planet was formed from those atoms, which were pulled together, forming our solar system and Earth, due to the effects of gravity. The elements that now make up the surface of the Earth were created in the core of the Earth through processes of gravity. The only reason the Earth has been habitable for billions of years is that gravity holds our atmosphere and oceans in usable configurations for life. The processes of evolution, developing organisms, occurred under the effects of gravity on the Earth. Just as you are, so also every other life form on this planet exists within a space produced by the force of gravity of planet Earth, and has existed the same way on Earth for 4.5 billion years. Each and every one of us is a product of gravity. Next time you feel the familiar press of the ground beneath your feet, the constant, quiet, unchanging force holding you to the earth, think about what that pressure means to you. Not as a force acting downward upon you, not as a constraint on you, or a means of keeping you from floating away, but rather as the history of 4.5 billion years of the universe, organizing itself, creating planets from dust, oceans from rocks, creating life from chemistry, and creating intelligence from life, all held together, shaped and supported by the curvature of space-time caused by the existence of mass. That is what we recognize as gravity. That is what it would mean to lose gravity. That is enough.